Hi, everyone. Look, it's my slides. So that's my real title, Jailbreaking Honda and Toyota Cars. You know why I picked Honda and Toyota? Because they're great cars. It's true. Ford, terrible. Don't buy a Ford. I also got to take 1 minute today. Today's the release of Taylor Swift's new album called Reputation. I'm a big Taylor Swift fan, so go out and torrent that or buy that. Yeah. What does a jailbreak do? So if you think about phones and you think about video game consoles, what does it mean? So the word jailbreak originally comes from, there used to be this daemon on the iPhone, I think it probably still is, called AFC. AFC is the Apple file system daemon, and it ran in a jail, which meant you could only access the files in a certain directory. It was a chroot jail. What the original jailbreaks did was break out of that chroot jail. But that doesn't really get to the meaning of the word. The meaning of the word is probably something along the lines of add functionality the manufacturer didn't include. So everyone knows what that means for phones and for video game systems. What does it mean for cars? Well, obviously the word jailbreak has the same definition. What functionality might you want in a car that the manufacturer didn't include? And another question, I get asked this a lot by the media. I used to do the phone jailbreaks, I did the video game ones, now I do the car ones, and they ask me why. And I give them the answer, but they never reprint it. I don't think they ever get it across very well because they don't really like it. Some people think, oh, it's to give consumers freedom. It doesn't have anything to do with that. Oh, you want to make self-driving cars to save people's lives. It doesn't have anything to do with that. Okay, oh, fine, you're greedy and you want to make money. No, it doesn't have anything to do with that either. It's for the love of the game. If I said that at Web Summit, it wouldn't have made any sense, but maybe here it makes some sense. Cool. So let's talk about car networks. Cars have miles and miles of wire in them connecting all of the ECUs. And you have ECUs for steering and ECUs for braking and ECUs, I think originally stood for engine control unit. Engines aren't controlled by ECUs anymore. They're controlled largely by PCMs, which is a powertrain control module. I don't know if it's like politically correct or something, but the PCM is what's, because hybrids and stuff. So you have car networks, and you have a bunch of different buses. You have CAN buses. CAN is this 2-wire differential protocol. We'll talk more about that. LIN, which is this 1-wire, pull it low, normally 12 volts pulled high, serial protocol. You have FlexRay, which is like fancy, and then in some new cars, you're actually starting to get Ethernet. But what is nice, so yeah, it's actually really great. If you want to find out about your car networks, there are huge repositories of information on the internet. They are paywalled, like $10 a day, $20 a day, but techinfo.honda.com, techinfo.toyota.com, these are just plethoras of information about your car. So it's cool. Imagine Apple had this. Apple kind of has this for the iPhone. You go to the developer page, and they show you what all the developer APIs look like. So techinfo.brand.com. So let's talk about the CAN protocol. CAN is a bus. So unlike something like Ethernet, which is not a bus, Ethernet is point-to-point, and then it uses hubs or switches or routers. CAN is a bus, so they're all actually on the same wires. It's a differential pair. It has a high and a low, and it has termination resistors on either side. And so only one node can transmit at once, and every node receives everything broadcast on the bus. At least it receives it at the physical layer. And this is true about Ethernet hubs as well. At the physical layer, you'll obviously receive every message, and that's what promiscuous mode does. It lets you get all the messages. But so then they usually filter them, and you can get at only certain IDs. So it seems like, I copied this from Wikipedia, it seems like there they call it the arbitration field. So in CAN, that's like an 11-bit message identifier. It kind of says which ECU sent it, And it's vaguely ordered by priority. So a message at address 0 gets delivered before, oh, that's why it's called arbitration field. Okay, that makes sense. So a message at address 0 gets priority over a message at address like hex 700. Then you have some control. The yellow is the length, and CAN messages can be between 1 and 8 bytes. I'm not sure if they can be 0, but I know they can be maximum 8. So you have these small 8-byte packets. And then you have a CRC, and you have an end of frame. So that's the CAN protocol, and it's used. This is the most common protocol used in cars for ECUs to communicate. So originally, if you want to buy, you can buy a lot of very cheap car dongles. This port is called the OBD2 port, Onboard Diagnostic version 2. And it's available in almost every car manufactured after 1996. You can buy cheap dongles on Amazon to interface with them. They come from China, and they have usually this chip, the ELM 327 chip. The ELM 327 chip was a PIC microcontroller. You know what? We should just bring it up here. Is my internet going to work? Well, that's bad if that doesn't work. I have a few demos. We'll give that a second. But yeah, so the ELM 327 chip, there's probably like 7 million of y'all on Wi-Fi. All right. So the ELM 327 chip was made by this one company, and the guy really put a lot of effort into developing this nice data sheet, and he was selling a PIC microprocessor with this code on it. This works a lot better if the internet works. Should have gotten a wire. Okay. Well, so okay, this is like. All right. So there's these ELM 327 chips. And they are what's in all of these cheap dongles. But the thing about them is they're 8-bit microcontrollers, and they're not capable of receiving all of the packets from the car. There's a lot of messages going on in the CAN bus, and you can't get them all. Come on, come back. Let's go. Okay, there we go. Yeah, so I'll show you this data sheet. It's actually a really nice data sheet. But yeah, so what happened is all of these cheap dongles ripped off the ELM 327 protocol because all of these apps started supporting it. So you get 7 million things calling themselves ELM 327, and they can't actually read the entire CAN bus. So what we did, and by we I mean the company I work for, comma.ai, is we made a better one of these. So you have like these, supports all OBD2 protocols. Yeah, if you only want to receive one out of about every 100 messages. One of the problems is it uses a serial chip, which only supports this ASCII interface. So we built something better. We used a 32-bit ARM microcontroller. We used ESP Wi-Fi chip. And we built this. All the firmware is open source. 3 CAN buses, 2 LIN buses, and a GM LAN bus. So this is a great way to get kind of universal access to your car. Not every CAN bus is available on the OBD2 port. So we also built this thing. It's called a giraffe. And it taps into, so down here, I have some screenshots from techinfo.honda.com. It taps into the CAN buses that are deeper in the car. Most modern cars have like 3 to 6 CAN buses with various things on them. The main thing that we can't get from the normal OBD2 connector is the radar. A lot of high-trim Hondas, almost all new Toyotas are actually shipping with front-facing radars in them. So you can get a radar and you can read all the messages off of that and see everything available, see everything that your car is seeing. So we have the bus, we have the interface. What's sent over the bus? I said it's these messages, 11 bits in normal mode, 29 bits in extended mode. That's kind of like the IP address. Then what's the protocol look like? Well, The way it usually works, this isn't always the case, but a lot of the stuff in the car, it's pretty nice. So this is a steering sensor message, and it's at ID hex 156, which means everything sent with arbitration ID hex 156 fits this kind of message spec. So you can see that there's like steer angle over there. It starts at bit 7. So they don't do endianness that well. Starts at bit 7, it's actually 765.0 and then wrap around to 15.8. But it is 16 bits long. And it is scaled, which means for every, so you can see like there's a unit there. That's what that degree thing is. And then for every 10 of the thing as an integer, it's 0.1 degrees. Well, negative 0.1 degrees because you flip the steering angle. So these DBC files are not available anywhere. They're not standard protocols. There's nowhere you can go to download the DBC files from the manufacturers. There are some standard API requests that are supported on every car, but those are actually active. So most of the stuff you've seen that interfaces with cars, like the Torque app or some of those scanners that will like get you the speed, they're using this active API. There's a whole passive API, which is what the ECUs in the car actually use to communicate with themselves. And that is what we are attempting to document in OpenDBC. So I'll go in here to OpenDBC. This is just a project on GitHub. Let me queue up this demo for later, just in case it takes a long time to load. So we have Acura, we have Ford, we have GM. So we can like look at what's on the Ford can here. There's just a huge amount of messages being sent around in the car. This one looks like there were actually leaks somewhere, so we have real names. So like a lot of reverse engineering, you don't get names. So you'll see this one is actually what, well, something calls them. I don't know where that came from. What's cool is anybody can contribute to this. But then you look at one we reverse engineered, like the Honda Civic, and this one has actually much more readable names. But these were reverse engineered. And we'll get to how in a minute. So that's OpenDBC. So what are we interested in? Well, what do you want to jailbreak a car to do? Let's revisit that question. I think one of the biggest things that cars don't ship with that you probably want is, well, to not have to drive. Right? You want the car to drive itself. Kind of really wasn't, why do cars have this like, think about it. Think about the API that we use to interact with cars. We interact with a car using a steering wheel, a gas pedal, and a brake pedal. Why? This isn't what we want. The API that we want to interact with cars with is like Uber or Lyft, right? You tell the car where you want to go, it shows up, and then it takes you there. So that's the API that we should expose on our jailbroken cars. So first we have to figure out so we're building an API layer kind of on top of the existing API. So the existing API has 3 things: gas, brake, and steering. So for the gas, there happens to be a message hex 30C. You can't control the pedal directly on the Honda and Acura, but you can kind of set the speed for the cruise control. And you can set the speed for the cruise control directly, and then there's a PI loop, which is all documented at techinfo.honda.com. PI, like PI controller, which you send at a speed, and it accelerates the car to that speed. So that is the gas pedal. For the brake, it's a little bit simpler. We have this message 1FA, and you just send it how much you want to brake, whether you want the hydraulic pump to run, and whether you want the brake lights to turn on, which is a little bit scary that you can send full braking without turning the brake lights on. And if you're rear-ended, it's never your fault. Seems like a quick way to do. Never mind. But yeah, so that's gas, and that's brakes, and then steering. There's actually a message in the Hondas that have lane keeping assist system to apply steering torque to the wheel. So if you send an E4 message, you can apply steering torque. How did we find this stuff out? How did we figure out which messages corresponded to what? Well, like any sort of reverse engineering, there's kind of two ways to go. There's a static and a dynamic, and everything is generally figured out with some combination of those two. But we've built a great static analysis tool for cars. And by static, I mean it actually runs on replays, so we log all the messages from the car, but you're not kind of doing it active. I think of almost everything in terms of like machine learning now. So this is kind of like the supervised version. It's not like the RL, the reinforcement learning, if you were doing it live. But so you reverse engineer with this tool called Cabana, and let's check out what it can do. I preloaded this, so it should be good. So here we go. We have a video from, why did that loop? We have a video here from our dashcam app, Schiffer, which is freely downloadable in the App Store and the Play Store. And it was paired to one of these guys here. Here's a panda. And the panda was sniffing all the messages on the car and sending them to the Schiffer app. So you can see here these IDs. Those are the arbitration IDs. And then what's that packet that we looked at? Steering sensors. So you see that it shows up here, MSB, LSB, and I can click here on steering angle. And I can zoom in here, and sure enough, if I go here, you're going to see the car turns to the left. And now you can expect it to go straight for a bit, and then you're going to see it make a left turn. Right about there, right? And then followed by a right turn. It's going to be in the middle of a right turn there. So that's what you can do with Cabana. Now, Cabana is not only for, so let's say I didn't know about this steering angle, right? Let's remove this signal. All I have is this. I'll remove this one too. So all I have is this blinking by as the car drives. I can click here, and I can drag a signal, and then I can plot it. Now, notice how the plot looks different. What did I do wrong? Who sees the problem? Well, it's signed, right? So I'll just go in here and set it signed. And then I have to do that because there's a bug. But now you can see the signal matches what you think the steering angle might be. You can also, so let's see, wheel speeds. So you can check out this. Here's the wheel speed from the front left wheel, and here's the wheel speed from the front right wheel. Let me drag this one on top of this one. You see how sometimes they differ? When would this wheel speed from the front left wheel and the front right wheel of a car differ? Well, they differ exactly when you're steering. So let me just rename this signal, steer angle. And sure enough, corresponds pretty well with when you're steering. Right, so you see how they, kind of hard to see, but at that bottom plot there, you can see that when they diverge, the steering angle is the largest. Now, if I've made changes to that DBC that I want, I can actually save it. Where am I going to save it to? Well, a fork on GitHub. So Cabana integrates with GitHub. You can save it to a fork and then actually commit it to your own version of OpenDBC. Then you can submit, once your DBC is ready for a car, you could submit a pull request, and you can get that merged upstream. So the plan here is kind of to crowdsource all of the message definition files from cars. We built a nice tool for it. Make it easy. Yes, that's most of what Cabana does. If you use our Schiffer app, you can do these all in the cloud. So this is stored right now in the cloud. This is just the demo route everybody can view. But if you log in, you can view your recorded drives. We also have real-time streaming. So right now it's not connected to a Panda, but if you plug your computer into your Panda, it shows up right there with web USB. Right now, the library we've released for Panda is a Python library. So Panda, all the firmware for it is completely open source. And the Python library to interface with it is here. So you just like create this class called Panda. And then you can like connect, you can reset it, you can reflash it, turn the things on and off, send CAN messages, send a serial port. So like I said, Lin just shows up as a serial bus. And then K-line is kind of a wrapper around that serial bus. They put a little bit of packing around it to deal with the fact that serial has no framing. So they have basically framing to serial. But yeah, can send, can receive and send CAN messages right over USB. We're also releasing very soon a JavaScript version of this library. So you get to access your car from a web browser. So you could drive your car from a web browser if you'd like. We just bought drivemycar.today, it's a domain name. I think that would be a pretty cool stunt. But yeah, so that's the Cabana demo. How am I doing on time? Cool. So for Toyotas, it's somewhat similar. The brake and the gas are combined into one message, which you can use to command acceleration. And this is much better, actually, because there's a lot of processing done on the pedal. One position on the pedal doesn't always correspond to the same amount of throttle opening. So as long as they do a good job with their command acceleration, which they have a pitch detector that's kind of janky. Obviously, you have to hit the gas a different amount depending on, if you're going uphill, you got to hit the gas harder, right? If you're going downhill, you hit it less to get the same acceleration because of gravity. But you can, command acceleration directly on Toyotas and then message hex 2 E4. So they added hex 200. Like I said, steering is apparently much more important to Honda than it is to Toyota. It's hex 200 later. But you can apply a lot more torque on the Toyotas too, so they're really nice. So this is it. This is what I've been working on for the last 2 years. It's called OpenPilot, and it is an open source driving agent. Because what good is a jailbreak if there's no Cydia? What good is an Xbox jailbreak if there's no nice launcher for games that you can download, or XBMC, or things like that? So what's the thing you want to install in your jailbroken car as well? I mean, you can do a lot of stuff with it, but we've been developing this. So we need some compute. How do we run OpenPilot? There aren't very powerful computers in cars. Most car computers, the most powerful thing, you're lucky almost even to get a 32-bit processor. You're finding these like 5, 10-year-old processors. I want something modern. So this is an Eon. This is one of the products our company makes. Okay, it's a phone in a case. But no, phones have it's a phone in a case. But phones have really nice processors. This is a OnePlus 3T. It has a Qualcomm Snapdragon 821. It's a very powerful processor, more powerful than probably all the processors in your car combined, unless of course you have a Tesla. Teslas have more powerful processors. But yeah, this is probably more powerful than everything in your car combined. And we don't exactly want to run Android on the phone. I looked into running Linux, but I mean, you can run Linux. I got Linux to boot on this, but then trying to get, it's graphics drivers that are really the killer. So when you start looking into this, there are binaries on this. So a lot of the kernel part of the graphics drivers are open source. Everything in the kernel is GPL. But the user space components, like the OpenCL compiler, is Android only. Android has a different libc from Linux. It's super annoying. Android uses this libc called Bionic, where Linux uses glibc. So we decided at the end of the day to go with Android. We have a fork of Android called NeoS, because Android is terrible. We ripped out as much of the Java as we possibly could, and we set up a really nice Linux environment. So here I am SSH'd into one of these Eons. It runs bash, like actual bash. In Tmux, you can SSH into it. Wow. Oh, I don't get it. I really don't get why the Android people invented all their own stuff. They have ADB shell. Why? Why not ADB forward and then SSH? Oh, it'd be so nice. Why do they compile this version of SH from like the 70s? You want tab completion? Oh no, they don't have that. So we actually got reasonable stuff to compile. Actually, a lot of this stuff comes from the Termux project. So there is this Termux project which has built this terminal for Android, and they've gotten they've put a lot of the patches in. So it was great that we could leverage all of their work. What does OpenPilot do? It emulates ECUs. We disconnect. The Giraffe actually disconnects one of the lower quality car ECUs and, well, replaces it with something better. So, I mean, if your phone can emulate a Game Boy, if it can emulate an N64, why can't it emulate a car ECU? And it can use all of its sensors and all of its compute to make the car better. So now let's show you guys an OpenPilot demo. I'll keep an eye out for the Eon, the Panda, and the Giraffe. I have to admit, I made the video for Web Summit. It's advertising. I'm sorry, I hate advertising. But yeah, so let's talk. See, you don't want to talk about that in an advertising pitch, right? I like this, it's a lot more real. The steering is highly torque limited. So while the car can drive well, really well on the highway, if we want to take this further and we want to make it drive around the city, we're going to need to get around the steering torque limit. But what's cool is that's just code in the EPS firmware. And then on some cars, throttle control is blocked at lower speeds. So you can't, although you can brake to go all the way to 0 miles an hour, some cars will call this like full speed or like full speed cruise control or stop and go cruise control. There's no fundamental reason why almost all the cars can't do this. Maybe the brake controller, maybe it's not great for the brake controller, but the brake controller will certainly come to a stop. And it's a decently smooth stop, almost rivaling what you can do. Probably beating most people actually. We have model predictive control in there now, which does really well. But yeah, this throttle control, I mean, the throttle is the most by-wire thing on your car. So steering and brakes are still physically connected. The brake controller uses, it's a pump to build up pressure, but you can also use your foot to build up pressure. And steering on all cars except for like one Infiniti is still a mechanical linkage, but we use the electronic power steering motor to actually get the EPS, electronic power steering firmware, to actually put torque on the wheel. So this throttle control limit is completely arbitrary as well. It's just in the PCM firmware. So what are these firmwares? The car manufacturers use this euphemistic term, calibration files. They don't want to call it car software. That's scary. Software's scary, right? Calibration files. That's fine. It's just calibrating. So this is the tool available from Honda to update the control modules on your car. And look, they even tell you most 2002 and later Honda and Acura vehicles have reprogrammable ECUs, which is pretty cool. I love when stuff's reprogrammable. So let's talk about the firmware on this. So this is the power steering controller from an Acura ILX. This one is nice. It's really easy to pull out. It's got these like 2 connectors, 3 bolts. And you look at the number on the outside, and then you can download this update. You can download this update package from Honda, and sure enough, it contains that. But it's encrypted. Uh-oh. So I looked at it for a little bit. I'm like, oh, encrypted. Okay, well, there's the encryption algorithm right there. So you can see that they used minus, XOR, and plus. Great, strong encryption primitives. And it's effectively just a monoalphabetic substitution cipher on the bytes. So, it's 1 byte as your width of a thing. It's 8 bits, that's not many. 2 nibbles. So this is the patch to raise the max torque. What's cool is you don't actually have to make code changes. There's just a table, depending on how much you want to raise the torque. If you want to raise the torque a lot, you might have to make code changes, but there's just a table. So it's that table at hex 28800. You just change that table and you can change the output torque. I can show you guys the table in IDA. We don't have that much time. So that's the patch. So now you got to put the firmware back, right? So get the firmware out. In this case, download it and decrypt it. And raise the max torque. Little aside, this is their checksum algorithm. This is not a good checksum. It adds the bytes up. So lots of, if you switch 2 bytes, they still add to the same thing. But don't worry, they have a good solution. They do it 4 times. Oh wait, it doesn't matter at all. If you switch 2 bytes, they all still work out the same. So don't do this. Please add a real checksum. If there's any advice I actually want to give to the car makers that maybe they can implement, please use like a CRC32. I just don't feel great about like reflashing my steering controller with something and like, okay, it looks right. Well, so actually my reflashing is fine because I do make one small code change. I changed one of the debug functions to be arbitrary read. So the flasher that I've written for the Acura firmware actually reads back everything and verifies it. The default one does not. A little sketchy. So putting it back, it's this custom, I don't know. I mean, you never actually know if something's custom. For all I know, there's like a PDF, you got to type in these special words in Google. But so you get this software. This was the dongle that I had at Tactrix. Now you can do all the same stuff with Panda. But I sniffed the bus between the Tactrix. The Tactrix shows up as a serial port. So I used a USB to serial. I built a serial proxy out of 2 Arduinos. And then, because I didn't know what the actual low-level stuff was, I was just trying to proxy it at the Tactrix level. But I proxied it, and I figured it out. If you spoof the version, you can get it to flash even when it already is the latest version. So that's what I did. I just spoofed the version. It was like, it ends in like 910. I just had to say that actually it's 900, and then I can replay the whole reflashing, which was nice, and I could dump the protocol. So how about the Honda Civic? Well, this one was a little more annoying. There was nowhere I could go online to download it because no update was issued. The only reason I could download the Acura ILX calibration file is because there was an update. But there was no update for the Honda, so how do you get it? Well, I mean, it's in there, right? It's in that one. It's 14 on the diagram. To make matters even worse, the Civic doesn't have a nicely disconnectable thing. It's the motor and the controller are one unit, and it's hidden way under the hood of the car, so don't brick it. So I bought a second one. It cost me $600, but I bought a second one of these things. It shows up, it's like a motor. I'm using a crowbar to get into it, you know, to like pry it off. Well, seriously, this is violent. It was real violent. But eventually I figure out what microcontroller it is. And it's nice. They had a data sheet. And the data sheet tells me about this command. Memory read. I love memory read. Oh, so okay, so I just have to figure out how to send this command to it, right? So yeah, I open the thing up, there it is. There's a Panda connected to it there. And I'm reading the data sheet, and I'm in. I get in. This is the responding to a version request, saying, hi, I'm here, I'm this chip. But then, I didn't read the data sheet all the way, and there's this. Before you can send the read, you have to send the key code checking command. It has a 16-byte key code. And I'm like, oh, this is going to be bad. How am I going to get this? All right, well, you guys, right here at Code Blue, I'm going to reveal for the first time what the encryption key is, probably to all the Honda ECUs. I'm not going to tell you how I got it, but maybe you can guess. So secret, it's 16 bytes long, much security, and there's the secret key right there. So, I was so happy. I was so happy. So I read a little thing to read it out. And yeah, there's the code in IDA. Something I really wanted to fix on the Civic. The Civic is nice. It has full stop and go cruise control, but you can't steer below 18 miles an hour. So sure enough, there's the compare right there, which checks to make sure it's greater than 28 kilometers per hour. So you just have to change that 28 to a 0. Again, a data patch. I feel kind of safer with data patches than code patches. So yeah. Now we got to put it back. Oh, I don't have the firmware. How am I going to do this, right? I don't have the firmware. I'm certainly not opening it up. I'm certainly not going in my car and opening it up. But fortunately, and I thank you, Honda, for doing this, it's standard. So there's a standard. It's called ISO 14299, 14229, I guess. There's 14230 as well, which has some more stuff too, but this is the standard set of services. Now, you see that one of them there is read memory by address. So why did I go to all the effort I did before? I just could have sent that. It doesn't work. I dumped the bootloader. There is no read memory by address command in the bootloader, but you can use this to re-download the firmware over what you have. So it's nice. Once you get it once, you can change it and you can flash it without having to do anything invasive to the car. And the best part about this is, well, so we're doing Toyotas next. And we're almost done with our reflashing procedure for Toyotas, and we're going to sell a $75,000 Toyota Prius that is modified to be fully drive-by-wire. But the way that we're going to make these modifications is just by reflashing 2 ECUs and including a free Panda with your $75,000 purchase. But what's nice about Toyota is there's already been a lot of stuff done. These are the OG car hacking guys, Chris Velasic, Charlie Miller. This PDF was very, very useful in my adventures in Toyota. So we're not going to go over too many details of Toyota, but we are going to offer the Toyota Crypto 300 Challenge. So everyone who might be interested, check out the paste bin. So the way this encryption protocol works is, it's like a monoalphabetic substitution cipher. Same as the Honda, except that there's 4 of them. And you have to do some like bit shifts to figure out which the 4 are, but that's all relatively straightforward. What's confusing is the way I got this out, so this is an S box. It starts over in the upper left at 00, 01, 02, 03, so on and so forth. So this is an S box, just like the S box is in AES. What's the pattern? The way that I got that out was by cribbing. I found big enough chunks of matching plain text ciphertext pairs. I did some frequency analysis, the classic crypto-analytic toolbox, and I did manage to recover this S box. If you go to the paste bin, there's 3 more of them as well. But I'm sure the key isn't actually that many bits of information. I'm sure there's not actually 256 factorial keys. So yeah, anybody who figures out what the pattern is, I will send you a free Panda. Yeah. The end game. Jailbreaking was the first modern app store. I was there in 2007 when, back in the day before modern phones, you had to get your apps on the computer. And then you could use Microsoft ActiveSync to download them over to your Windows phone. The same thing was true with like J2ME apps on the Razr. You couldn't go to a URL and download them, or you couldn't open an app to install other apps. The first modern app store was called Installer, and it was only available on jailbroken iPhones. I've even heard rumors that the App Store would not have existed had the jailbreakers not made one first. If you watch Steve Jobs' presentation of the iPhone in 2007, he's talking about how there will be no apps and how everything developers want will be HTML5. So was it a bluff? Who knows? It's Apple. I'd love it if someone actually knows, by the way. If you guys remember for the original Xbox, I love this thing, XBMC, Xbox Media Center. To everyone who was a bit hacker inclined growing up when I was, we had Netflix 10 years before everybody. I had all I used to watch like Malcolm in the Middle. I had all the Malcolm in the Middle episodes. You could watch them. This was Netflix, but 10 years before anybody else had Netflix. It was, again, the same people, the same jailbreakers. So now let's show the car industry the future. Let's build on top of their platforms, and let's build better stuff than they can. There's still lots to do. So more car support. We've recently gotten pull requests for Chevy and Tesla. These are people not working with us, anything except for externally in the community. They've managed to port OpenPilot to their cars and jailbreak their own cars. Better car support. Who wants to do the PCM mods? I showed you guys today how to do 2 EPS mods. Vaguely showed you. There's enough information there that you should be able to reproduce that if you're so inclined. Who wants to do the PCM mods? PCM mods are a whole lot safer than EPS mods too. Because what's the worst your car's going to do if it accelerates at the brakes? Improvements to NeoS. So Android custom ROM hackers. It's an Android ROM. We just made our own custom ROM. It's a nice environment, If you want to do anything with like Android kind of deployed, these things are incredible embedded computers. I don't know why anyone buys a Raspberry Pi when you can buy for the same price like a smartphone with an LTE radio, a nice GPU, same $40. These things cost nothing. Okay, this one costs a bit more than $40, but. So yeah, improvements in NeoS, ports to other phones, that kind of stuff. We have a community. There's about 1,500 people in there now, slack.comma.ai. If you're interested in following up with any of this stuff. And here is where cars are different from phones or video games. Every time you'd come out with an iPhone jailbreak, every time I would come out with an iPhone jailbreak, I did 3 of them, Purple Rain, Black Rain, Lime Rain. They would last at most a few months before Apple patched them and everybody moved on. Or even when I found ones that were permanent, Lime Rain was permanent. You couldn't patch Lime Rain. But you could ship a new phone next year. And then Lime Rain slowly became irrelevant. Smartphones are replaced on average every 2 years. Cars are replaced every 9 years. And the bane of jailbreakers' existence, there's no OTA updates. Tesla is the only shipping car with OTA updates. So if you do manage to jailbreak cars, this is a long-term victory.